let me start with a short introduction to my system. The motivation to this sensor system is to measure density and viscosity independently with the same measurement system. Due to the special actuation scheme for the levitation and the rotation actuation, we can measure density and viscosity independently. There are a lot of benefits for this system in use because there are no bearings and high precision drives necessary for any measurements. It is resource saving due to the small chamber size of about 6 millimeters diameter. It is also for all fluids except ferrofluids. And yes, now I want to describe the measurement setup. I want to start with the backbone of the system, which is the top and the bottom body of the system. This bodies contains the measurement chamber, the space for the levitation actors, and the inlets for the fluid, and the space for the oscillation actors. The next thing is the floater magnet, which is here a sphere with a diameter of 2 millimeters. The next part is the levitation actor. Two of them are built in the system, as you can see. It contains the levitation coils and the Hall sensor for the measurement of the position of the floater magnet. There are also readout coils for the rotation on the levitation actor. The next parts are the X and Y oscillation actuation coil bodies, which contains the coils for the actuation and for the oscillation and afterwards the rotation. The last thing of the mechanic parts of my measurement setup are the additional permanent magnet brackets. Yeah, these parts are used for the whole measurements. And now I want to describe the density measurement principle. Here we have the two levitation coil actors, the levitation actors here and here, and the levitation coils. We have two Hall sensors nearby the floater magnet, which measures the position of the floater magnet itself. Due to the actuation of the coils to hold the measurement body in the middle of the measurement chamber, we have influence of these on the measurement for the position of the floater magnet or the measurement body. So we have added two Hall sensor outside the levitation actors, which nearly measures the influence of the levitation coils and the influence of the digital PID controller, which regulates the position of the measurement body. Yeah, we also have two permanent magnets for a higher magnetic field and higher forces in our setup to reduce the current in the levitation coils. Yeah. In case of a measurement, there are acting three forces on our measurement body. The gravity, the buoyancy force, and the force due to the magnetic field. Here we see the controller output to the reference density. And you can see that the absolute value of the controller output is decreasing with higher densities. The other thing we want to measure is viscosity, and therefore I want to describe the measurement principle of it. Here we have the the coil bodies and the coils in Y and X direction, which can put the floater magnet into rotation. At first, I want to describe they put the floater magnet into an oscillation, and if the oscillation in X and Y have a phase shift of 90 degrees, the torque around the z-axis is a result of it. And this torque leads to an rotation in the z direction, or around z direction. Sorry. This we have animated. As you can see here, we have the magnetization direction of the floater magnet itself, and the flux densities in X and in Y direction. And this is how the floater magnet rotates around the z-axis, as you can see here. This rotation can be read out with two coils. They are located here and here at the levitation actor. Here we can measure induced voltage, which is modulated by the rotation of the permanent magnet. This rotation frequency is checked with at first with an optical measurement system. Yeah. The next slide shows you the induced voltage, the FFT of the induced voltage. As you can see, this is the oscillation frequency, which is the excitation, and sorry, the two rotation frequencies which are modulated on the signal. We already checked out the dependence of the actuation, the rotation frequency to the actuation amplitude in volt, peak. And as you can see, from 5.5 to 7.5, the rotation frequency of the floater magnet increases linearly with the actuation amplitude. We also made some measurements with different viscosities, and the behavior of this you can see in this slide. You can see that with increasing viscosity, the rotation frequency decreases. At last, I want to give you a short outlook of the system. We want to control the temperature of the fluid in every measurement. We want to increase the range for measurements for higher viscosities. We also want to increase the resonance frequency of the system, and we want to make the resonance frequency electrically tunable. So that was all. Thank you for your attention, and now I'm here for questions.